Each group will be given a maximum of 30 minutes to present, after which it will be followed by question and answer session, which will involve the other group as well as the panels. The panels today will be from myself and Pak Aulia as well as Kak Devita. During the presentation, so all presenters, the members of the group should turn on their videos. Should please turn on their video, and then during the question and answer, also the asking group should also turn on their videos. Any questions before we start the presentation?
Sir.
Yes?
No.
No questions? Okay. So today is Tuesday, 29th of June. Okay, so let's start with group 1 first. Yeah, group 1 will be presenting first, and followed by later question and answer. So you have 30 minutes maximum to present. If you stop earlier, that will be also okay.
Sir.
Group 1 is siapa? Ezra and
Angeli.
Okay.
Sir, ini ini my laptop kameranya error. Is it okay if I switch to my phone?
Yes, sure. Or you can log in from both laptop and phone.
Okay.
Sir, belum ini host masih disablein.
Oh ya, sorry.
Paling hanya urutan soalnya sama, urutannya beda. Jadi ada bang soal. Pokoknya kita ini apa aja? Ya aku juga mau buat ya.
Okay, is Angeli ready? Angeli?
Masih coba join serang di handphone.
I haven't seen the other account at the waiting room.
Masih connecting sih. Oh, udah deh, sir.
Soalnya kan Jawa itu lockdown di Jawa Barat. Jadi sekolah lama sudah masuk DKI sudah masuk Jawa Barat ya? Nah, kalau udah namanya lockdown, semua pesantren tidak boleh dikegiatan.
Okay, where is the other Angeli? Yeah. Okay, please start anytime you are ready.
Okay, good afternoon, everyone. So today, Angeli and I will be presenting about our final projects, which is fabric-based PCR microfluidic chamber for DNA amplification. But before we explain what we did, I want to remind us what kind of problems that our seniors faced. So the previous problem in the previous study is there are three aspects. The first one is about the chamber, sensors, and also the heater. So the chamber means that the functionality of the chamber has never been tested. What I mean by that is that it never been tested to the DNA. Um, but it has been tested for the hydrophilic and hydrophobic part. And then the second one is the sensor. So the CNT sensor is inaccurate, and they said that it is because the lack of characterization and also because of unstable resistance. And then the third one is about the heater. So they use two kind of heater. The first one is the CNT thread as heater, and the second one is nichrome wire. For the CNT thread as heater, it cannot reach more than 75 degrees Celsius. So they change it to nichrome wire. But in nichrome wire, it is unable to accommodate temperature change. So the jumper wires is burned when it changed from 95 degrees Celsius to 65 degrees Celsius. So by those previous problem, we propose solution, and that will be explained by Angeli.
Okay, so for the solutions that we propose, first is regarding the chamber design. So we improve the design to enhance the microfluidic properties. And then for the CNT thread sensor, we change it so that the cotton thread will be braided before it is dipped in order to increase the CNT absorption and lower the resistance. After that, it will be sewed onto the fabric to stabilize the resistance. As for the heater we will use two strands of wire that will be twisted together and then shaped into a sinusoidal wave with amplitude of 1 centimeter. Additionally, both the sensor and heater will also be characterized before they are used. And here is the modified chamber design. It has the dimension of 7 centimeters times 7 centimeters, consists of 4 layers that will later be folded. And then on the right is the complete design with the CNT-coated thread as sensor and nichrome wire heater. For the materials and methodology, first here are the list of materials that we use. And next, for the methodology, first is the manufacture process of chamber. So the cotton fabric is cut according to the dimensions and the outline is drawn. After that, we use previously printed vinyl sticker paper to cover up the hydrophilic parts. And then we prepare a mixture of epoxy resin and hardener with ratio of 1:1. And then the mixture is poured onto the hydrophobic parts and spread equally. And then the chamber is dried for 16 hours until it hardens. After it is dry, the steps 4 and 5 are repeated once more to make the chamber more solid or harder. And next, for the sensor fabrication, the first step is the preparation of CNT solution by taking 5 grams of MWCNT with 500 milliliter of distilled water. The solution is sonicated for 30 minutes and then magnetic stirred for another 30 minutes. For the dipping process, 3 strands of 30 centimeter scoured cotton fabric thread are braided, and then the strand is dipped into CNT solution and sonicated for 30 minutes. After that, the strand is dried in an oven at 60 degrees Celsius for 10 minutes. And after it is dry, we measure the resistance. If it is still too big, we repeat the dipping into CNT solution. For the characterization of sensor, here is the setup. We use candle to generate heat that will be detected by the sensor, and then while the resistance is measured by the multimeter. Next is for the heater. As I've mentioned before, it will be shaped like a sinusoidal wave, like here in the red circle. And then it will be characterized with the help of NTC thermistor. Next. Yeah, it will be characterized with the help of NTC thermistor as the temperature sensor, while the heater is provided heat by a power supply. And next is the circuit to control temperature, which we integrate both the sensor and the nichrome wire.
So now I will discuss about the result, and we will say about the discussion. So I will say it one by one, from the microfluidic chamber first about the manufacturers. So in here in figure A and B, I'm sorry, 1 and 2, the left side and the middle one, is the result of the chamber. So the A part is the unfolded one, and the B part is the folded one. And inside the circle is the hydrophilic part, and outside of it, outside layer is the hydrophobic part. And after we did the manufacturer's process, then we think that to hold the chamber nicely, so we created casing from cotton fabric. And why we choose cotton fabric is because it can be tightened and also it can be loosened easily. And we just have to sew the edges of uh, the casing like this. And another reason why we want to use casing is because small movement can affect the resistance of the sensor, and because the sensor is sewed to the fourth layer, in the fourth layer. So we want to hold um, the sensors and also the jumper wires. And also when we manufacture the chamber, the amount of epoxy solution that is used to cover the the cotton need to be small, because if it's in the big amount, the epoxy will spread out to the hydrophilic part and close the hydrophilic part. So this part was some kind of difficult, because we failed many times, but after all we did it. And now I will discuss about how to test the chamber. So the left side is the prediction of microfluidic system in the chamber. So the dark blue colors represent DNA, the yellow one represents PBS, and the green one represents the primers. And these solutions will be put to the in the first layer, and then after that, um, the DNA and the primer will bind together. Will both All of the solution will flow to the second layer. However, the DNA and primer will bind together and mix in the that is represent with the Tosca color. Uh, and after that, after they are mixed, the solution will go through the third layers. So in the third layers, it is where the PBS and also the mixed DNA primer will mix together, and it becomes the red colors, which is mixed PBS and DNA primers. And in the fourth layer, as I mentioned, and Angeli has shown the picture, the sensor will be sewed in the fourth layers, and also the heater will be put on the bottom of the fourth layers to maximize the heating process. So the heat will directly go to the third layer. And on the right side, this is the chamber result. So in here, because we tested using water plus food coloring, so the food coloring that we use is yellow. So we see that in the hydrophilic area, it is stained by water solution. However, in the hydrophobic area, there are no yellow color. So this means that this chamber it can be used um, and have hydrophilic and hydrophobic properties, good hydrophilic and hydrophobic properties. And then now we move on to the CNT-coated thread sensors. So first is the fabrication. So Angeli mentioned that we dipped and sonicate 3 times, and each times we did around 30 times, 30 minutes, I mean. But in the reality, we did a lot of dipping and sonicating steps, because we made a lot of threads. And the reason why we want to achieve small resistance is because when we sewed it, some of the CNT will fall off. So the resistance will become bigger again. So we have to make it very small. And when we process, it still becomes small. And after it was done, the thread will be sewed on the fourth layer, like in the right pictures, and the edges of the um, sensors will be twisted together to the jumper wires, and after that, to make it stable and still, uh, we glue it using glue gun, so um, it doesn't move easily. And after that, we did characterizations. And in this characterization, we did this setup. The reason why we did this setup is because we cannot go to the laboratory, so we have to use properties that are available at homes and simple equipments. So we use can. This is wait a minute. This is a can, and also candles, and also this is the sensors, and this is the NTC W1209. This is the multimeters, and also this is the NTC itself. And after that, we try to um, make an environment for the sensors, so to make a proper experiments. So by doing this setup, we use radiation system from the candles and also the aluminiums of the can. So the sensors and also the NTC will catch the heat that are radiating from this plate. And also the distance between these sensors and the plate, both of the sensors have the same uh, distance, and between the sensors and the plate is just 1.5 centimeter. This is because we want to eliminate many external factors that may be occurred. And also when we did it, we cover the surrounding of uh, the can, so we don't get the external factors like wind, something like that. And we set how can we set the heat is by um, variating the candle height. So we there are 3 points temperature that we use, which is 40, 60, and 80. Actually, we want to use 60, 80, and 100. However, we cannot make the environment like until 100 degrees Celsius, because the candles melt easily, so we cannot get like the stable 100 degrees Celsius. So we change from 100 to 40 degree Celsius, and the distance between 40, 60, and 80 is just the same, which is 20 degrees Celsius. And to arrange the heat, we as I mentioned before, we variating the candle height. So for 40 degrees Celsius, the candle's height is 3 centimeter. For 60 degree is 4 centimeter, and 80 degree is 5 centimeter. So it become higher and higher, and sometimes the fire will um, go up and touch the aluminiums, and it will radiating heat more. That is how we control the heat. And these are the results. So basically, it is I really want to say that characterizations of the CNT-coated thread is very hard, because slightly movement can change all the resistance, and we have to repeat it again from zero, and we kind of face that kind of problem. So we repeat it again and again and again, but finally we can capture good um, results by not touching it when we do the characterization at all. So the the temperature that we get is like the average is 31.2, 44.9, 92.286, and 79. And then the average is 40, 38, 36, and 35 um, kilo ohms. And this is the graph, temperature versus resistance. So we know that the anti-coated thread is the NTC. So that means that when the temperature is increasing, the resistance will be decreasing, and the proof. This is the proof. So after that, after we get the result, we go to count the coefficients to be entered to the Arduino. Um, so these are the values for the coefficients that will be put in the Arduino. Next, we go to the nichrome wire as heater for fabrication. So the fabrication is like this. So this is the results. Angeli made it, the nichrome wire. So she twisted and she arranged it to like the sinusoidal wave like that. And at the end of the edges, she soldered it with the um, jumper wires, so it can easily connect it to the relay for the full experiment. And now is the to test the heater. So there are two different experiments that we conducted. So the first one is to know how much voltage that is needed to reach temperature until 100 degrees Celsius, and we tested from 2.4 volts, and 2.7, 3, 3.3, and also until 3.6 voltage. And after that, we get 100 degrees Celsius, and we average it, yeah, approximately 98.93 degrees Celsius. And because of that, we use 3.6 voltage as a reference voltage for doing the next experiment, which is we want to know the time required for each of the PCR steps. So how much time the nichrome wire need to get to the temperature that is needed. For example, for denaturation is around 95 to 96 degrees Celsius. So the time that is needed is approximately 2 minutes. And then for annealing, it's just 59 seconds, 55, 57. And for elongations, it just need from 65 to 75 to 80 degree is just 20 seconds, 21, and 18 seconds. So it's kind of fast for the changes. Uh, and because the PCR also needs a fast time to change like that. So now we go to the full test. So the setting for the full test is like what we drawn before. So we need Arduino, power supply, step down, relay, solder stand, CAN and also NTC W1209. And why do we need CAN is to eliminate, once again, it's to eliminate the external factors, because inside the CAN is in this picture. So the NTC is also used to become reference, and also this is the nichrome wire. I'm sorry, it is quite small, but if we look at this, there are nichrome wires and also the CNT-coated thread as sensors. And these are the codings. We use the previous code that our seniors made, and we change it a little bit. For example, is the okay, so we change it a little bit to become, for example, is the coefficient. I'm sorry, for the coefficient, we put it the new one and change it. But overall, it is the same with the what our seniors did. So wait. Okay, so now we discuss about the result of the full test. So when we arrange it, um, we let's see the video first. Look, I'm sorry. Okay, so I'm sorry, maybe it's the video cannot be opened. So in this video,
And
it
can you not
shows that
use
the
the
relay.
original? Can you not use the original video file rather than the one in PowerPoint?
Yeah, yeah, okay. I'll show it later. I'll explain it first. Yeah. So in basically in this experiment, we already assembling it like what we has planned before, and we see that um, the heaters can work well. However, in this test, we found that the Arduino cannot read the sensors. It's the result is like this, that minus 27 273.28 Celsius. So it means that it closely to zero, closely to zero. So we tried by changing it to the temperature, to the resistance. However, it's still not good. Um, but when we test it to the multimeter, it can reach nicely. However, if we put it to the Arduino, it still cannot read uh, the temperature. So basically, for to be honest, we cannot do the full test because of this problem, and because the time constraint that we got. So that's a big problem, and we think Anjali and I discussed about it, and we think that the problem is about, and we found maybe the problem is in the circuit itself, because when we change it to the resistance, the resistor, I mean, it still cannot, the Arduino still cannot read uh, the temperature. So we the problem is in the circuit itself. So wait, maybe I can find the full video. The video is shown just the full, like um, show that the relay can, I'm sorry, the heater can work in that circuit. So it's from 39.9 and then it become 40 like that. But as I mentioned before, the problem is like that. So now we'll discuss about the obstacles.
So for the obstacles that we face, first of all is with the CNT-coated throat sensor. We first, actually at first we proposed a zigzag design in order to enhance the length without taking much space, but it is too hard to be sewed onto the chamber. And the other main problem is that it is very unstable, the resistance of the sensor during the characterization step. As for the nichrome wire heater, first we wanted to use the coiling design, but when we use it, it is hard to increase the temperature, meaning it takes a lot of time to reach a certain temperature. So eventually we change it to the sinusoidal wave design. For the full experiment itself, first we change again the nichrome wire, the size. Initially we used the one with the amplitude of 0.5 centimeters because when we test it during characterization, it is fast to increase the temperature and yeah, like that. But when we apply it to a full test, the heater did not give sufficient radiation to be detected by the sensor. So we change it again by increasing the size into amplitude 1 centimeter, which is bigger. Next.
Okay, so but before we finish, because there are times, so I want to discuss about the problem. Maybe this is what we this is the hypothesis that we find. So we created this kind of um, circuit, but because it is voltage divider, it should be connected between the pin 2 and the resistor. So maybe we haven't tried it, but maybe that's one of the problem that can affect the results of this. And that's the thing that still in our we want to improve it more if we have time later on. So that's all from us. Thank you.
Okay, thank you, Anjali and Ezra. So first, I would like to welcome Pak Aulia to give some questions, discussion. Pak Aulia.
Yeah. Okay, thank you, Pak Dedi. So hello, Ezra Angeli.
Hello, sir.
Yeah, you did a lot of experiments and just answering your or questioning your last circuit problem. Can you go back to that slide?
Uh, this one?
Yeah. So what is actually the circuit configuration? Is it just directly measuring the voltage there, or is it a voltage divider, or uh, what do you need?
Okay. Because the Arduino cannot read the resistance, so we the input is should be voltage. So we make voltage divider between the resistance in the CNT and the resistor in we already know the resistor in here, which is 10 K. So we want to know the resistance change in the CNT. Therefore, we use voltage divider um, to be so the Arduino can read it.
Okay, so as the laser point is pointing in the middle between pin 1 and pin 2, So we can assume in between there is a resistance. Um, how the voltage divider works is actually the A0, the blue one, the blue wire, should be connected to the pin 2 where the laser pointer is pointing. If it's point using like that, then you are just going to have 5 volts. You won't measure any difference in the resistance.
Yes, thank you, sir.
Okay.
We just realized it.
Uh-huh.
We
I've seen
just
it before.
actually we made it, but yeah, but we made the full test yesterday, so we still confused what is the problem, and now we found that, oh, maybe that's the problem. So we want to try it. Hello, sir.
Yeah, Pak
Okay.
Aulia.
Yes. Sorry, I think the signal here is a little bit difficult. Um, and about the relay, can you explain why do you need a relay over there for the nichrome wire?
Maybe Angeli can explain it.
So basically, the circuit is will be used for PCR, right? For PCR, for each step there is different temperature. So basically, we use the help of the relay to control the temperature. To accommodate the temperature change, so that if it is too high, it will based on the microcontroller, it will based on the microcontroller programming. If it is too high, it will lower the temperature that is given in the heater, like that. So,
Okay, the other benefit is actually the power source. You have 5 volts. You can have it from external power source with bigger current power, so that you can give more energy to the nichrome wire. That's maybe one of why you cannot control when it's in a what is it, spiral configuration, is it?
Actually, we also use the external power supply, sir, from the
Uh-huh.
relay. This one, the
Okay.
from the nichrome wire, the 3.6 volt. It's from a power supply that is stepped down.
Okay. Next, my question is about. Can you go back your slide? Go back again. Where you have the can. Yeah, I think. What is it? Is that one?
This
So you
one
have the can.
can.
Yes. Or where you have the NTC, you have the can, and then you show the NTC placement.
This one.
Yeah, on that one on the left side. Yes. So the NTC is measuring the temperature on the can or inside the can, or it's a bit difficult to see in this angle.
Okay, sir. First of all, I'm sorry. It's because if we move it, the resistance will change again. So we really don't want to touch it. That's why the picture is like that. But the NTC read the heater, so we know when the heat uh, is maybe 60 degrees Celsius, the resistance is maybe 38 kilo ohms, something like that. Not inside the can.
Okay.
But
Okay.
why we use can is because the surrounding is full of wind, so we want to keep it uh, close, like
Mhm.
that.
Okay. Yeah, if your circuit was correct with the voltage divider, you will have lots of data for measuring the resistance changes on the CNT because of the different temperatures. Okay, Pak Dedi, I think for me,
Thank you, sir.
that's all.
Thank you, Pak Aulia. I
Thank
would
you,
like
Reza.
to proceed further to Kak Devita. Maybe some question from Kak Devita.
For the time, Pak Dedi. Okay, guys, I want to ask you about was asking about the circuit. Uh, well, actually, it's still continuing the Paulia's question, yeah, about the voltage divider. Why did you decide to use voltage divider instead of Whetstone bridge? Maybe can you explain?
Okay, so we use the voltage divider basically to find out the resistance of the current, because in the coding we need that the we need that second resistor in order to calculate the temperature, because we use the Steinhart-Hart equation, which requires the R2 in order to give out the temperature, because the sensor cannot automatically give uh, the Arduino cannot automatically read the temperature from the sensor. So we have to use R2 before using calculations to change it into temperature.
So the voltage divider is the best way. Yeah, it's the better. Voltage divider is better than another method like Whetstone bridge or etc. etc. Yeah. Have you researched about this? Yes. Yes.
Basically, why we choose the voltage divider is because it's easy to um,
Implement. Yeah.
implement, yeah, and because there are a lot of problems like sensors that is the resistance is very unstable, and the heaters we haven't tested yet, and we choose the simplest method to just use, so we can concern for another problems that we faced like that.
Okay, then I will go to my next question. About the chamber, yeah. Have you guys already tested the chamber? Maybe using color liquid. Just want to make sure that the hydrophilic is really works and didn't spread everywhere. Have you guys already
Yes,
tested? Yes.
yeah, yes, we already tested using food coloring, yellow food coloring.
Yellow. Only yellow. Yeah, because
uh
here you are. It's supposed to be three color, yeah. No, no, four color or five.
yeah,
Uh,
um
it,
Yeah,
yeah. That's
yeah,
our mistake. uh
yeah. I think it is better to you to also input the result of the chamber test in your PowerPoint. Yeah, not only like this.
okay,
Okay, okay. I think that's all
okay,
from me. Thank you.
thank you,
Yeah,
Kak Dev.
that's it.
Thank you, Kak.
Yeah, good suggestions from Kak Devita ya, to include the results of any of your experiments to your presentation and report. Okay, then I would like to ask the group two, Andy and Tanita, Grace, to ask questions.
Um, could you please explain the coefficient part, because I'm a bit confused. Hello, hello. Can you hear me?
Yeah, yeah, easily.
Sorry, di sini rada
Anita.
nge-lag soalnya videonya.
Okay.
Ya itu ya, why there are different coefficient and how do you put it later for the Arduino?
Okay, so for the coefficients, we need like 3 points of temperatures to be used. So we use 44, 62, and 79. Uh, 40, 60, and 80 as the point, and the average is for 40 is 80, 38, and so on. So we enter it to the Steinhart and Stein calculator. So basically and it produce the point where A, B, and C, like this.
Okay. Yang buat di Arduino code-nya kayak, can you show me kayak where to put that
Oh,
coefficient?
okay. So wait a minute. The code is the C1, we change it in like this, and C2, and also the C3. So yeah, we just copied it from the results there. And then next, this code will be processed in wait a minute, in the entry temperature. So we use the Steinhardt and Hart equation. So it's just uh, uh, 1 divided by C1. So C1 is taken by the coefficient 1, and then plus C2 log R2 plus C3 log R2 times log R2 times log R2, like that. And then this will produce the temperature. However, it is in Kelvin, so we reduce it by 273.15 and it will produce the temperature itself, and it will be
So
written.
so kalau di Steinhardt equation emang there will be 3 equation that relates to one another ya.
Yeah.
Okay, thank you.
Andy, maybe any question?
Could you please go to the table where you show the data of heater? Yeah, this one. As we can see, the attempt for 3.6 voltage, it shows 100 degrees Celsius, right? And it shows lower value to another trial. I mean, like, are you sure that when you use this, when you implement this to your device, the heater could withstand the heat? I mean, like, they could provide the right temperature, since perhaps due to overheat, it could break the heater and it will not give the right temperature.
Anjali, you want to answer it?
Okay, so basically, because the required temperature, the highest is about 95 to 98. So we have to use the voltage that can reach up to that temperature. That's why we use 3.6. And when we test it here, we don't. There isn't. We did not. We did not find any problem on raising that with the wire when we raise it to such high temperature. So we conclude that it can withstand the high temperature and that we can use it, because if it burns or get destroyed or something, then it means we have to change something again with the wire to in order to accommodate the highest temperature. So yeah, based on this test, we conclude that it is suitable for use as a PCR. That's why we use it at the 3.6 voltage. Yeah, because we want to reduce the time also so that it can reach the desired voltage higher. Is that it?
Andy,
Okay.
satisfied?
Yeah.
Yeah.
Okay.
Okay, no more questions, Andy, Tanita, Chris. Okay, yeah. I would like to ask some small questions. So basically, you have not yet proven that you can achieve a cycle temperature regulation. Have you?
Yes, sure.
No or yes? I mean,
No, we still not
Haven't
test it.
tried.
Yeah.
Yeah, we haven't
Conduct the full
because
test.
the previous full test was unsuccessful. So
yeah.
we
And
have to
the main reason of that failure is what? What is the main reason?
Our hypothesis is the we put the wrong cable in the circuit, so
Yeah.
it cannot read the voltage divider. That's the problem there. So that's what we suggest. That's what we think right now, and because we still not try it, so that's just the thing that we think it is the
Okay.
problem.
The chamber that you are trying to heat up and control the temperature, if you made it from the fabric now, if you put your heater, your nichrome heater, as well as the CNT-coated thermistor underneath the fabric chamber that you made.
Yeah. Yes.
So, so what is the function of the can just now? That can you show again your setup? Yeah, if possible, yeah, the picture, yeah, the photograph should be clear, yeah, clearer, yeah, than right now. Yeah. This is not clear. I mean, it looks very crowded, and maybe it is better also if you provide the schematic next to the picture, so we know what is what, yeah, in your setup here. So you are doing the thermal regulation in the can or in the fabrics chamber.
In the fabric chamber, sir.
So where is it now here in this uh, setup?
That one at the bottom of the can. Yeah, right.
So yeah, and wait a minute. So this black one is the CNT sensor,
Yeah.
and because the nichrome wire is so thin, so this is the nichrome wire, but maybe it's hard to be seen
Yes, it is.
even when I'm sorry, sir, but even when it is
In real life,
in
it's
real
all
life,
yeah, it's all hard to see
yeah,
because it's very very thin, the wire.
What is the function of the can here?
um, block the wind.
Block the
Oh, yeah,
wind.
yeah. So maybe it can um and to create the same temperature.
Because a can
So
will is very conductive, heat conductive, right? It will release heat easily to the surrounding atmosphere. So maybe
yeah,
when you heat up your fabric chamber, some heat is gone through this can to the surrounding air. Is it good or is
okay,
it bad?
maybe
Yeah.
um
It depends on on the design actually. Yeah. If you want, you can discuss with some groups in the lower batch in the your junior in the first year students. Some of them have project also for making thermal regulation in ECR, although not in fabric-based chamber, but rather in any chamber. I make it free for them. They designed several types of chamber, some using aluminum can also like that. So there is a plus and minus there. And usually also we discuss about heat loss, etc. So
okay,
the heat going from the can may be good if you want a very quick cooling. But if you want, so during the cooling step, but if you want to have a quick heating up, it may not be that good, yeah. So because then some heat will be lost through that metal can. It's not contained within the chamber, so it may take some time to heat up the fabric chamber. So that is plus and minus of that.
okay.
So I don't see also you are incorporating any Peltier cooling system, for example, here. Yes.
We didn't use like Peltier cooling system because it is very fast to change from 100 to 60 degrees Celsius. So because of that, we think that we don't have to use it.
Mhm.
Yeah. Unfortunately, it is not shown here. Yeah, the data you mentioned when it is very fast. The cooling down.
Oh, this one.
This one, sir.
Okay, so the which one? The right table
The,
or
the right table.
sir.
okay?
Yeah.
So
And,
first, yeah. So
and
first,
the left table
the
is showing what?
the left table showing different how much temperature.
Various temperature that can be reached when we supply given voltage. Yeah, different voltages like that.
Okay, so this is more of calibration, calibrating the heater. The left table.
Yeah. I'm sorry. And the right table, yeah, to see how much time does it need it required
Yeah,
to.
it may be wiser to separate them as separate
Okay.
table rather than one because they are about different things. The left one is about testing the component, the heater only. The right one is already as a system, as a PCR system. So it's better to make it separated as a separate table, yeah, not within a single caption. Okay, you understand what I mean?
Yes.
Yes, sir.
Next is that I would like to have it more like this, yeah, time. Then you really show us the graph when it goes to 95, when it is the denaturation, and then going to 50, when it is at annealing, and when goes to 65, sorry, elongation, yeah, annealing, sorry, and then going to 75 or 80 when it goes to elongation. After which it goes back again to denaturation. This is what I would expect to see actually. That you can successfully regulate the heat at the fabric fluid chamber like this. This is temperature, the y-axis temperature, the x-axis is time. So then so not a single data like this, but rather we can have from 0 to denaturation, this is the time required. So you can take different time. From denaturation to annealing, what is the time required here? From annealing to elongation, what is the time required here? You can put also average between this and this. Yeah, so this is first step, second, third. First, second, third. Then you can have average of them after you graph them as a temperature versus time in the chamber, in the fabric-based chamber. If you successful in this, your project get A. And because this is the idea, if you can do this in water, it means then you can do that next semester for PCR, real PCR. But for now, it is still a component-based characterization. Heater, like that, initial temperature. Yeah. It is one. Yeah, you are measuring only one, but it is how many? Yeah, like this or triple trial. But this it can be in cycle. Yeah, and simulating, for example, the PCR of the SARS-CoV-2 until CT25, CT40, for example, means for 25 cycling, 40 cycling. That is your goal. Yeah, actually, during using the Arduino to control that in that chamber, fabric-based chamber. Is it achievable or not? What do you think?
Gimana, Anjali?
Maybe.
Right now, we we want to
Depend
know
on
that if the full test can conduct well or not. But if it's can
But
conduct
if
well, maybe yeah,
it
I'm sure we
succeeds,
can do it.
yeah. If
Mm-mm.
the full test is successful.
Yeah, so be careful with your voltage divider design. Choose the resistor, the series resistor carefully, and then test it as a cycle like this. It's the main goal of your project. I don't ask for real PCR amplification, but it's still thermal cycle of water inside that small fabric based chamber. If you can do that, that is already something good. Okay, so please take into account all our inputs from myself, from Pak Aulia, from Pak Devita, from your colleagues, yeah, and put it into your report. Yeah, and we will have some time until submission of the report. Thank you, Group 1. That will be all for Group 1, Ezra and Angeli. Let's proceed immediately because not much time to
Thank you, sir.
progress. Yeah,
Thank you, sir.
thank you. So let's proceed with Group 2, Grace and Andy.
So good afternoon, Pak Dedi, Paulia, Kadivita, and friends. Today, I and Andy are going to present about our project, which is the contactless temperature sensor based on CNT-coated thread IR absorber. So previously, our seniors had done this before, and judging from the reports that they had made, I think that there should be some improvements needed in this project. So yeah, we made some improvement here, such as enhancing the sensitivity by changing the lens use, and also to make the bolometer small. And also we do some quantitative experiments, yeah, so that we could see clearly the resistance at each temperature. So our aims is still the same, which is to create a bolometer. So what is a bolometer? Bolometer is a temperature sensor that could detect infrared radiation, because heat could also exist in form of infrared radiation, like for example heat from the human body that exists in the mid infrared wavelength range, which is around, I think it's 10 until 12 micrometers. And inside the bolometer is an anti-thermistor, which is in which we use MWCNT COOH coated thread. This has been proven before by our seniors that it could act as anti-thermistor. Next. So what is anti-thermistor? Anti-thermistor is a resistor that could change and the change is affected by the temperature change. So when the temperature increase, then the resistance will decrease and vice versa. So that's why it is stated that the resistance is inversely proportional to the temperature. And the resistance and temperature has a logarithmic relationship. So like it could be seen from the graph on the right side. Next. So from the NTC thermistor, we could only observe the resistance change. So how do we automatically detect the temperature change? That is by using a transducer, which is in which we plan to use whetstone bridge. So the resistance change could produce voltage difference. It means that here at the R1, we will put the thermistor, while if, for example, this one will become smaller, then the VA and the VB, the voltage here could change. And then the voltage difference could be detected by the Arduino and then converted back to resistance. Why this is important? Because Arduino couldn't detect resistance change, so that's why we use the voltage. And then from the voltage, we could change it back to the resistance. And how do we do it? By using this equation here, the equation 1. So the whetstone bridge is simply like a parallel circuit, like the R1 and R3 is parallel to R2 and R4, while R1 and R3 is series to each other, and R2 and R4 is also series to each other. So if there is a resistance change in the R1, then for example, if it becomes smaller, then VA will be greater than VB. Under this condition, the R1 and R2 should be the same, and R3 and R4 should be the same at the equilibrium state. Yeah, so that's the condition, and that is determined by the resistor that will be chosen. Yeah, so from this formula here, we could obtain the resistance change of the thermistor that is affected by the temperature change. Next.
So for the materials and fabrication, as we can see, there are several materials and equipment that is bolded because those are, we can say it is important, the most important one, because as for the HBN sediment, it acts as we can say it helps. Yeah, it actually helps um, the sensor to absorb the IR radiation. So the HBN sediment will be coating the fabric. And for the MWC and TCOH powder, it will be used to coat the thread that will be act as the sensor, and the thread will be sewed into the fabric that is coated with HBN. And for a Fresnel lens, we this is the difference between our experiment and previous batch. They use the F the zinc zetonite lens,
Selenium.
zinc selenium, sorry, zinc
Yeah,
selenium
if I'm
lens,
not mistaken.
and we use Fresnel lens here. In order to we think that it could increase the IR absorption for the sensor. And the bolometer casing itself, it is important. Why? Because we need to construct the casing that can help the sensor to get the right place for the lens to directly enhance the IR radiation, so that the sensor could work that we want greatly. Yeah. So to make the MWC and TCOH coated thread, first we need to scour the thread by using sodium bicarbonate added in distilled water, and then it was heated until 90 degrees Celsius, and then we put the thread in it and stir it, and then we get the thread, the scoured thread. And then the thread then will be cut into fragments of 15 centimeter long, and then it will be braided to help reducing the resistance. And we prepare the MWC and TCOH by using MWC and TCOH powder. We mix it with distilled water, and then after we mixed it, the solution will be sonicated, and then after sonicated, it will be stirred, and then we can get the MWC and TCOH solution that can coat the thread. Then the thread will be coated by that solution by putting the thread into the solution of MWC and TCOH in a beaker, and then it will be sonicated to get the until we get the result, a low resistance result, which around 10 kilo ohms until 30 kilo ohms, so that when we suit it, it won't increase that much of resistance. And then we fabricate the fabric using we coat the fabric using HBN. First, we extract the BN sediment, and we mix it with the distilled water. And after we mixed it, we sonicate it, centrifuge it, and vacuum filtration it. Why? Because we need the residue of the solution, so that we use this 3, 4, and 5 step. But from our result, we didn't we actually find the residue, but it is so small, a small amount of it, so that, and it can't get taken from the filtration paper, so that we use the supernatant one. And then after that, we immerse the cotton fabric into the supernatant. And then we get the HBN coated fabric. So for the sensor fabrication, firstly, we marked it first with ballpoint uh, or something that can mark. And the thread stitched into the fabric, and then we tied it at both ends because we don't want it to get away from the fabric. And then we put the heat shrink to cover the wire thread connection so that it will be steady. For the bolometer, we have the first and second design, and we actually use we will be focused on the first design because the second design it has specialty on lock and lock design, but it failed. But we could still use the design, and we put it at the gap of the sensor for the second design here. As for the first design, it will be tucked between the upper and the lower part of the casing. As for changes, the lens hole, we adjust the lens hole into 0.2 centimeter height. Before it was 1.0 centimeter height. And this is the bolometer casing that we made at Tinkercad. This is the hole for the vacuum placed on the bottom part of both design. The first design is the yellow one, and the second one is the red and blue one. And the hole, we adjust the hole too. The hole for the jumper wire, we placed it differently. This is the left side and this is the right side. And as for the first design too, so the vacuum, it will be using the straw. It will be placed here, and the jumper wire will be placed here and here, both left and right side. And the front part will be the straw, the vacuum.
So I will be discussing about the experiment and results. First is the MWCNT-COOH coated thread themselves. So first, after we sonicate it for about 2 times 20 minutes, we got a resistance of around 10 kilo ohms to 30 kilo ohms. So the resistance produced is unpredictable. So yeah, we could gain for different threads, we could gain different resistances. But then we didn't directly sew the thread to the cotton fabric. So we put it like we left it like for, I think it's 3 days or 4 days before sewing it into the cotton fabric. But then the resistance changed again. Yeah, and then after that we stitch it into the onto the cotton fabric, and then the resistance changed again. So for the further experiment, so we choose only 3 threads, and these are the resistance after being kept for several days. So for sensor 1, it is around 54.1 kilo ohm, sensor 2 is 39.5, and sensor 3 is 28.15 kilo ohms. And then after they are being stitched onto the cotton fabric, their resistance increase to this amount. Yeah, they have we couldn't predict the resistance change. Yeah, that's what we conclude from the experiment that we have done. Yeah, so the sensors will then be used for will then be calibrated. Next. So first, for the sensor calibration experimental setup, so why the calibration is important? It's because we need the beta value and also the reference resistance of each of the sensor, so that the Arduino later could help in in detecting and determining the temperature automatically. This will be discussed further by me later after this. So the three sensors are calibrated to a 10 kilo ohm NTC thermistor of the W1209 thermostat. Um, this one this is the sensor, the NTC 10 kilo ohm NTC thermistor, and as we can see there are two crocodiles wire that are attached to the both end of the sensors wire, this one, and this is connected to a multimeter. So we isolate the sensor inside a box, inside isolation box. Actually it's the Peltier box, and there's also the Peltier module and the W1209 thermostat, which means that they could automatically control the temperature. But at that time, during our visit to the lab, there are some problems, so we couldn't use the W1209 thermostat as it should be used. Like, so we only use it to display the temperature, and we should control the temperature manually. So the temperatures that we in which we use for the calibration is 15, 20, 25, 30, and 45. And how do we maintain this temperature? For the hot one, for the warm temperature, which is the 40 and 45 degrees. I'm sorry, that's there are addition itu ada 35 and 40, but yeah, I forgot. It's my mistake. I didn't write it. For the above 30 degree, we use like a hot water filled inside a beaker glass, so that the temperature could increase. As for the cold temperature, we use a what's that ice pack. So the resistance will be measured for 120 seconds for each temperature, and the resistance changes will be, the resistance displayed in the multimeter will be noted for each 10 seconds. Next. So as I have mentioned before, it is very important, the calibration is very important to determine the beta value. The beta value, could you please show the beta value? Yeah, beta value, and also the reference resistance. So what it means by reference resistance and also the T0 here, they are both the reference temperature and resistance at room temperature, which is 27 degrees Celsius, or for this equation we use 300 Kelvin. So the RT, the equation above here is the NTC thermistor equation, the given NTC thermistor equation. That is a logarithmic function, but then we could change the equation into its linear form, and yeah, it could be derived into the equation below. So for the so we use this equation later to aid us in determining the temperature automatically using Arduino. Yeah, and that's why it is very important for us to find the beta and reference resistance value, because they are different for each sensor. Next. So first, these are the resistance and versus temperature graph for sensor 1, sensor 2, sensor 3, and thermistor. So we also measure the thermistor's resistance for comparison. Yeah, actually, the thermistor, the blue one line here is a bit curvy, like the one that I showed in the early part of the presentation, yang rada melengkung ini, the NTC thermistor curve, but because of the range, the Y range here, the line appears to be a bit flat. Yeah, so as we can see here, the resistance decrease as the temperature increase, and this means that the sensor is feasible to be used as NTC thermistor. Next. And this is the calibration curve. So here, this is also the linear regression that we have calculated, that is calculated through Excel. As we could see here, the one with the highest beta value means that it is more sensitive towards temperature change, and it is obtained by the thermistor, the 10 kilo ohm thermistor that is commercially used. Next is the sensor 2, because as we could compare here, it is 0.0533 compared to the sensor 3 and sensor 1. This has the bigger value, which means that it has the best sensitivity among these three sensors. Next is the sensor 3, and the third one is the sensor 1. So that's the calibration curves. And then next, and then this is the results, the equation, and also the beta value and reference resistance. So as I have mentioned earlier, the beta and reference resistance is different for each sensor because it has their own characteristics. From the graph that I have shown earlier, the resistance versus temperature, it could be concluded that the MWCNT-coated thread is suitable to be used as NTC thermistor. And sensor 2 is the most sensitive among the 3 sensors, but not the NTC thermistor. But even though it's the most sensitive, it has a very low sensitivity when compared to the NTC thermistor. But even though it has quite a wide range of beta value, it doesn't mean that the sensor couldn't be used to measure temperature because it could also have resistance change when the temperature change. And the next is the sensor is reproducible. This could be proven by the 3 sensors that we have made, and we could also prove that the sensor resistance will decrease if the temperature increase and vice versa. And the sensors are able to detect in a temperature range of 15 until 45 degrees Celsius. Next.
So for the calibration of the thermometer, we want to make sure that the thermometer was actually working well. So we calibrate it at 0, 20, 40, 60, 80, and 100 degrees Celsius. And then we want to obtain the linear regression, which is in here, the Y. And we want to make sure that why we want to get the linear regression so that we could use it to calibrate the bolometer. So as for the example in here, when we want to measure 10 degrees Celsius, we could just change the X, and then we could know that the thermometer will show the 12 degrees Celsius. The thermometer will show 12 degrees Celsius. And then we want to calibrate the bolometer. This is the setup where the heater placed up suspended above the bolometer, and it not have any contact, so there are space in here. So we use the calibrated thermometer to measure the beaker here, and it was suspended above, and then the temperature we use is 10, 20, 30, 40, and 50 degrees Celsius. And we measure the resistance, same as the sensor before. We used 2 minutes, and each of 10 seconds we record the data. And actually, this is we want to actually use sensor 2 and sensor 3. However, I think we think that the additional jumper wire here affecting the resistance result, which makes the result unreliable, so that we change it into another sensor, and then we just used one sensor due to time. So we use one sensor and then we calibrate it, and we obtain the data here. Why we actually plot it for only 10, 20, 30, and 40 while we get until 50 degrees Celsius data? It is because, as you can see, at 50 degrees Celsius, it is not theoretically right, so that it will break the linear regression. It will ruin it, so that we exclude this, so that we only plot it into 4T. And this is maybe the fact that this bolometer can't measure the temperature above 50 degrees Celsius. But this bolometer, because we just only tested into one sensor, and 1 millimeter. So to prove it, we need to take much more data on it. And then we obtain the calibration curve, the linear regression, which is beta value equals to 0.0095, where our reference is 63.886 kilo ohm. And as I said before, we only use one sensor, and as I said before, the resistance above 50 cannot comply with the theory. So we just plot for data. And to take attention in here, it is only in this bolometer. I mean, like we need to take another experiment so that we could prove is it possible to measure above 50 or not. And this video is taken and fast forwarded 2 times for the sake of time. So I've tested it using my hand.
Andi, can you maximize itu gak gitu kelihatan?
Oh, okay, sorry. So I tested it using my hand, and as you can see, the resistance value isn't working well. It shows only 57.7 kilo ohms, and it is not moving at all. So I think it is for now it is quite not reliable due to some problems and encountered.
So to conclude everything, the next slide. These are our problems that we have undergone through all of the experiments. First is the unpredictable resistance changes, like I have explained before, like after sonicating, and then we left it for several days, and then after that we stage it, the resistance change unpredictably. So yeah, we could yeah, that is also a problem. And then second is the HBN residues, which fail to form with unknown reasons yet, but then we use the supernatant. Third is the experimental setup. So for the calibration of the sensor, we should control the temperature manually. It means that we should open and close the isolation box, and maybe it could also affect the temperature inside the box and also the resistance. So for the next experiment, I think we should really like close the isolation box without having to open and close it and to adjust the temperature manually. Why we don't use oven? Because the oven temperature range could increase like from the designated temperature. For example, it's 60, then it could increase into 62, 63, 64, and then it will later make the resistance keep on decreasing and decreasing. And the last one is the decreased sensitivity of bolometer. As it could be seen from the beta value, the beta value, I'll take one example, like from sensor 2, it's around 0.05, the beta value. But for the bolometer, it's around like 0.0095. Yeah, as we can see, there is a wide difference of beta value, and it means that the sensitivity of the bolometer is far below the sensor only itself. So I think there are some problems like the lens being used or the connection between the wire and the thread that could also affect the resistance change. Next. So for further improvements, first we would like to isolate the sensor properly before being placed in bolometer. It means that this is done to prevent much resistance change. So like we put it inside a plastic bag or inside something that is isolated and not expose it to the environment so that the resistance will not change that drastically. Second is to ensure tight connection between sensor and wire, because if there are like some movements, I think the resistance could also change and become unstable. Third is to evaluate the lens being used, because it could probably be the reason why the sensitivity of the bolometer decrease. And then fourth is to improve experimental setup and also do a repeatability test. So why is repeatability test important? Because we will want to use that bolometer again and again, it means that it should be reusable. But due to the lack of time, we couldn't test this repeatability of the sensor. So that's why for further improvements, we would like to test the repeatability to test to see whether whether the bolometer is feasible to be used more than one time or not. Fifth is to connect the bolometer to the Whetstone bridge and Arduino, as I have explained earlier, which is where the Whetstone bridge is used as transducer. We were able to do this step because um, there's no time. So yeah, for the further improvements, we would like to do this test, but after we could make sure that the bolometer has a stable resistance and good resistance change, so that yeah, the result will later be also good. Next.
So for the conclusion, the MWC NTC coated thread could serve as NTC thermistor, as we can see from the data before, and the sensor was reproducible. However, it has different reference resistances. And in this experiment, I think we think that there is something bad, that is something needs to be improved on the casing bolometer, like from the lens and the sensor, and several things as mentioned before. And this is the timeline where we conduct the experiment and others. That's all from us. Thank you.
Okay, thank you, Andy and Grace. Yeah. Okay, I would like to request Pak Aulia to ask maybe questions.
Okay, thank you. And Andy and Tanita, you did a lot, and then you created the case by yourself. Is it correct? The
Yes, sir.
bolometer.
And
And is it so?
in the case,
It was 3D printed,
Yes, sir.
and then were you able to vacuum it?
We
Is there a need inside to be vacuum?
yeah, so that the temperature, I mean, yeah, it will not affect the resistance change from the temperature yang transmit above the bolometer yang through the Fresnel lens. So yeah, as the previous batch also said that it should be vacuum, but we are not really sure for the vacuum part whether it's totally vacuum or not. So yeah, it should be further experiment. We should do further experiment for that.
Next is about the circuit to measure the resistance. Yeah, where is it? Okay, so are you happy with the result of the Whetstone bridge?
actually we haven't implemented, sir, because we want to actually find whether our sensor works well or not. So so for the further improvements, we want to implement it for the circuit.
So without the Whetstone bridge, does it work?
Yeah, it does. It did work, but the thing is, the reference resistance could change gitu. Jadi kayak misal it's around 60 at the first trial, and then we leave it, and then when we try it again, the resistance could change. Jadi kayak itu belum stabil and it needs to be solved. The problem should be solved first, gitu.
Okay. So if you're going to use a Whetstone bridge, then you are expecting little changes in the resistance. Is it correct?
Correct. Because karena beta value and the reference resistance are determined are determined at the calibration. But then later if itu kan will be used for the Arduino code, and then later if that change, then the result will also change gitu. The temperature will not be correct. Yeah, something like that.
Okay. Next is so when you acquire it, you use ADC from the ADC is from the Arduino, is it?
Yeah.
Yes.
Yes.
Yeah.
Is there any data that you were able to achieve?
For the Arduino, not yet. We actually have the code from the previous batch, but yeah, we haven't tested it for this one. But we know what to do. Like the VA and VB will be connected to the A0 and A1 of Arduino, and then yeah, we make a circuit like it is at the Whetstone bridge, and then it's similar to Ezra's work actually, but Ezra didn't use the Whetstone bridge. Yeah, we intend to use the Whetstone bridge, but we haven't tested. Yeah.
Okay, so my final question is about the video that you when you capture the results. Yeah, can you explain what happened? I mean, what are you expecting? Is it the resistance changes or what is it?
Andy, explain.
Oh, yeah, we actually wait, sorry. So as Tanita mentioned before, that NTC thermistor works where the resistance change was due to the temperature change, and body temperature is around
36,
20,
30.
yeah, 36-ish. And from the data that we've taken, it actually changes. Where is it? Oh, we didn't actually put the data, the lots of data, but it is on the appendix on um our report. So so there are actually changes on around 36 degrees Celsius, and while in here there are no changes. I mean, perhaps it should be our forehead or something, maybe parts of where usually people do the measurements, but just to test it using hands in here, they don't have any uh, changes in resistance.
If
And
you
it is
touch,
for like 30 seconds. This is fast forwarded 2 times.
okay,
Huh?
if you touch the sensor directly, does it change the resistance?
Uh, I haven't tested because I mean, if we touch the sensor, then so the sensor itself is a sensor that can have resistance changes due to pressure, so we can't actually touch it, the sensor. As for as for to touch the lens, I mean, I think we intend to make the sensor that passive sensor. So
Yeah. Okay.
oh yeah,
Yeah.
so
What I mean is the temperature sensor when you use the change in the resistance, right?
yes,
What is it called again?
bolometer,
NTC.
Kilometer.
NTC. Yeah. When you touch it directly and then plug it to the multimeter, is there a change in the resistance or not? That was the question.
Yeah. You mean without the bolometer kan, kayak the sensor directly we touch it.
Yeah, correct.
There is resistance change.
Oh, okay, the NTC. Okay, okay. Then I think that's it for me. Thank you, Andy and Sarita.
Okay, thank you, Pak Aulia. Kak Devita, maybe some questions?
I have a question. How many tabs did you open in your browser? Wow, so many. Sorry, out of topic ya.
Kedengeran, sorry.
Oke. Yang
Iya,
penting nggak nge-lag aja, yang penting jangan sampai nge-lag.
Enggak. Kecil aja suaranya.
Oh, oke.
jangan dilihat itu, Kak.
Okay, my question is, what is the use of container? Okay, you open the right slide here. So my question is, what is the use of container here?
Container, is it this one?
Yeah,
Yes.
peltier
Yes,
one.
of course. Yeah. What is the use of it?
So we want to conduct experiment where our sensor will not have any other outer what do you call it? Outer
Pengaruh.
yeah, that
Outer.
affect the sensor. So we closed it in this isolation box. Actually, there is the uh, top
To
of it.
eliminate the external factor.
Yes, the external factor. So we want to make sure that it is safe right there and with no any other um,
Unwanted
goyangan.
factors.
Yeah,
Yeah.
unwanted factors.
Yeah.
So we put it inside the isolation box.
Okay. Okay, that's correct. But why did you not using such a container in part of bolometer calibration?
As for the bolometer,
Yeah.
we want to measure it through the lens, right? So it is something like something like IR thermometer. Like we want it to
Yeah.
measure,
Sure, yeah,
yeah,
directly.
from the heat source. Yeah, so we we use this setup, not that, because it is contained in the casing too. So
Yeah,
it
but are you sure that the temperature of the beaker glass with the water is same? The external factor, of course, can affect, right? Especially for the heat coefficient of the Pyrex and water are different. You know about that? Yeah, I
Yeah,
think,
but uh,
yeah, I appreciate that. I believe that this is the best that you can do, yeah. But I think this is not so accurate to calibrate the sensor, how you calibrate the sensor. Especially for the sensor calibrating system, when you are using container, did you use such a fan cooler or anything to make to have the heat can distribute to all the points of the container?
uh, uh,
Yes or not?
no, there are no fans and there are no fan and yeah, actually there's a thermostat yang itu yang di ujung yang ada merah-merah LED. Actually we could use that to control the peltier, yeah, to control the temperature. Tapi for some reasons, yeah, at that day we couldn't use it for that function
Yeah.
gitu.
So
So,
yeah. Okay.
but
So
there's no fans, yeah, no
there's
fan.
no fan. Okay.
Mm-mm.
So if there is no fan, so it means that the position of the sensor will affect the heat reader. I mean, the sensor to read the temperature, right? The closer one to the system, to the beaker glass or to the cooler will be read more accurate, like that, isn't it?
Yeah.
Yeah. So I think the position of the sensor is different, yeah. Okay, so the position should be the same.
Yeah.
Harus dikondisikan ya.
Mm-mm.
Yeah, because the distance is different, so the accuracy of the sensor will be different as well. I think like
Yeah.
yeah. Hmm. Okay. I
Thank you
think
for the
that's
input,
all. Yeah.
Kak.
Okay, I think that's all. Thank you, Andi and Tanita. Thank you, Kak Dedi.
Thank you, Kak Devita. So, okay, I would like to request Group 1, Ezra and Angeli, to ask questions.
Okay, I want to ask, you said that you left the thread for several days and the resistance is was changed, right? And in your opinion, what factors that cause that uh, phenomenon?
Andy, you would like to answer?
Okay. So uh so we put when we left it left the thread, we actually want to make sure that the thread wouldn't have increase in resistance because of the powder is what is it, mengelupas, yeah, so that
Yeah.
if that happened, then the resistance increased. So we contained it at plastic bag right there, because actually at that moment we do it at home too. So yeah, we intend to have to minimize the factor where the MWC and TCOH mengelupas from the thread. And yeah, that is one of the factor where the thread resistance increased. It is due to the mengelupasnya MWC and TCOH from the thread.
Actually, yeah, that's our hypothesis, but yeah, should be tested further again.
So ditinggalin kayak gitu sengaja. Bahasa Inggrisnya apa? Do you
In purpose.
yeah
In purpose.
No.
No.
No, it is actually not. It is
Not enough time. So yeah, we should go home and do
yeah,
it again. Or
and it is like Kamis, Thursday, so we can't do the experiment directly, isn't it? If I'm not mistaken, is it Kamis?
Yeah.
Is it Thursday? Yeah.
Yeah, I forgot ya. But we cannot do it at the same day. Pokoknya at that time
Yes.
here. So that's why.
Okay. But if you already finished to make thread and the thread is already dried, my opinion, you have to sew it right away directly, because that will help the resistance not to change. Like what I did, it doesn't change even though I apa namanya, nindih itu secara unintentionally,
Okay.
but it doesn't change widely like that.
Okay. Yeah, we'll try it later. Yeah, thank you for the input.
Anjali, any question?
Stone bridge, is there a specific reason that you have to use with stone bridge, or is it possible to replace it with maybe something simpler, like a voltage divider that I use in my own project?
The reason why we actually use Whetstone Bridge is because yeah, we have read the our seniors report, and yeah, they write about the Whetstone Bridge, and yeah, I search about it, and yeah, that's also a good idea, although it's a bit complicated. And yeah, basically it's apa namanya, basicnya kan kayak paralel, kayak voltage difference gitu, voltage divider juga. It's commonly used everywhere, so yeah, we decide to use this one, even though maybe we could also use the one like your model gitu, which is more simpler. Yeah, I think
Okay,
yeah, it's like that.
Okay, Anjali, are you satisfied with the answer? And Ezra? No further questions from group 1?
Sir.
Okay, yeah, okay. So I have several questions here to group 2. First is regarding the changes of the resistance after stitching. Did you take a percentage of change of the before and after?
Oh, we didn't count the percentage. Yeah, we only
That is the
relatively,
problem.
but, yeah.
So we cannot really judge whether the resistance the resistance change was consistent or not. You cannot
Okay.
make sure that the resistance always the same for every processing. But what you can assess is whether the change in percentage is similar or not. But I see now here, maybe it changes about less than 10%. Yeah, less than 10% of before to after. I think that's fairly good enough. Yeah, so you have to assess it like that, not based on the absolute value of the resistance. In sensor and measurement, we often do not use the absolute value of the parameter, like intensity, resistance, etc. Rather, we use relative changes. Similar like with gauge factor, for example, in strain gauge, we express it as delta R over R0. You still remember or you forget? Yeah.
I remember, sir.
The delta R over R0. If it is delta R,
Yeah.
you will have, of course, different changes between one sensor to another. But delta R over R0, usually they are almost similar between one sensor to another. They are repeatable, reproducible. Okay, so you cannot judge directly just based on the absolute change like this. Okay, next on the calibration.
Which one? The volumeter
Wait,
or the sensor?
Next slide, please. Okay, next. Yeah, okay. Here, so what we do is usually we make averages between triple, quadruple, or quintuple measurement, or sextuple, or seven. What is quintuple measurement? Yeah, so we do not just calibrate sensor 1, sensor 2, sensor 3. No, we calibrate it using average. You draw like this, and then you use use the same temperature points, right, to calibrate all this.
Yeah.
Yeah. So then you can just draw a single calibration curve. You put then the standard deviation for each of the point. I have explained this in sensor and measurement class. Yeah, if you review again the videos, you forgot about this. Calibration is not just with a single sensor. You can do with a single sensor, you can use multiple measurement also. If it's a single sensor, you use multiple measurement, of which you will get standard deviation. You can combine different sensors calibration, so you will have then the SEM, standard error of measurement from statistics. Then you have also the calibration curve, you have the standard deviation. From there, then you can determine the precision of the sensor. The precision or the detection limit of the sensor in temperature. So from here, then you will know what is the minimum temperature that the sensor needs to feel such that there will be a resistance, readable resistance change based on the standard deviation at the background measurement. Background means could be the room temperature, for example, room temperature measurement, or could be at 0 degrees Celsius, for example. Yeah, you forget. So this is the importance of theory and the importance of paying attention to the class. Don't sleep during the class. Or importance of reviewing the video after the class. If you don't review, yeah, you forget. That's why I record and I put in the Google Classroom for you to review. Okay, you get no. So you cannot draw just a single like this without any standard deviation at each point. Look at any paper in journal. They will have the standard deviation at each of the measurement point in the calibration curve. It's never drawn from a single measurement. You understand? Next, please. This is the this thermometer, yeah, okay. For the calibration, okay, good. Yeah, so yeah, before I think Kak Devita's point is valid. What you are measuring is the temperature of the water. What is felt by the bolometer, what is seen by the bolometer is the temperature by at the outside of the Pyrex glass beaker. Okay, so yes, it is influenced by the temperature of the water inside the Pyrex, but you should it has its own also insulation properties, right? The glass beaker. So its temperature will not be the same as the temperature of the water. So actually, to be accurate, yeah, your this temperature thermometer should be put outside here, attached to the outside part of the glass beaker. You control its temperature by heating the water or cooling the water inside of it. Yeah, but the temperature being seen, because you are developing a contactless temperature sensor here, it sees the infrared radiation by the subject in front of it, by the object in front of it. And in this case, it does not see the water directly, but rather there is beaker in between. There is air, but from the air we can neglect it. Right? But actually, it is also correct from Kak Devita. It will be more precise, more accurate. You put it inside the thermostat, so there will be no other influence from the wind, from the surrounding, from your own temperature, because you are measuring next to it, near to it. It can also have some influence, yeah, even though it's very small. Okay, the setup needs to be carefully designed. Do you understand? You get it?
Yeah.
Okay, yeah. So you should have measured the temperature of the beaker outside the bottom part of the beaker glass, not the temperature inside the beaker, because you are measuring now. What you are measuring now is the water temperature. Okay, so that's why your calibration may not be accurate. Then. Okay, go next. Yeah, so similar with the previous calibration, so this should be done also with multiple measurement, cannot just be a single measurement like this. Actually, it is okay that you don't get temperature beyond 50 degrees, because what we want to develop is contactless body temperature. So the range of our temperature is between, let's say, 30 to 40 degrees. You should have actually the point of your temperature should be within this 30 and 40 degrees. No need actually to go to 10, 20, or 50. But you need to have a higher precision. Yeah, a higher precision to be able to go actually at 0.1 degree, yeah, for body temperature. And yeah, this should be, there is basically from this chart, yeah, there is a good trend, right? There is a possibility that it actually works. Okay, but also it is not convincing as a data. You need to do at least 3 times of this data at multiple data. Similarly, you have to draw the standard deviation. Even within a single sensor, you have to do the calibration multiple times. You could not just calibrate one time. No, at least 3 times, so that you can draw the standard calibration. It will be best then if you want to know the overall processing. Yeah, so this is standard deviation. If you do from triple devices, triple barometer, what you will have is SEM, standard error of measurement between different. That is showing already the reproducibility, while standard deviation showing the repeatability. So this is a little bit different. It's from statistics. Yeah? So you have to incorporate also your statistical knowledge from Pak Fatoni. Okay, next. Yeah, here also. So if, can you go previous slide, please? So from here, you know that the bolometer calibration curve is, let's say, every 10 degrees Celsius, it is going down by how many degrees? About 1 degree,
One.
1 kilo ohm, right? About 1 kilo ohm. So let's say when it is just about 5 degree, so the half of kilo ohm. Go to the video now. Enlarge it, please. So what is the unit there?
Kilo ohms.
What is this unit?
57.7 kilo ohm.
Pause, pause, pause.
Kilo ohm.
Huh?
That's kilo ohm. 57.7 kan di?
Yeah,
Why there is zero
57.7
here?
kilo ohms.
So 57.7 kilo ohm.
Yes.
Is it? Okay. So yeah, I would expect the change range maybe in hundreds of ohm or less than hundreds of ohm. Yeah. So you have to, before your hand above it and when your hand above it. So it will be, the room temperature there is 25 degrees, right? Change to 37 degrees. Then the change is 12 degrees Celsius, but you have to allow it to have some what you call it, some time also to change. So maybe it is too big also, the scale here. So rather than using a multimeter like this, it would have been wiser if you use your own system to amplify the signal, the delta R. The multimeter is not is without amplification. If you use Arduino your own, you amplify, yeah, either with some bridge or voltage divider, doesn't matter, you do amplification. Then you can see that the changes. You might, because your calibration shows there is a change. Go to the left, the previous slide, please. The calibration, previous slide. Yeah. Your calibration shows indication of the bolometer works. Although it's not convincing because you have just done it once. But it shows that there is possibility that it works. So only it could have been done better because now you don't have any amplification at all. You measure it directly with multimeter. Actually, at the beginning, I also already suggested to two of you, based on the experience by the previous batch, to use active temperature sensing. You remember or not? Active temperature sensing, you flow current into the thermistor, and then you measure the current change based on the absorbed heat. Theoretically, maybe should have more higher sensitivity theoretically, but we don't know. At least, actually, your junior is trying to make 3 groups in your junior, trying to develop an active temperature sensing for this application, for their electrical engineering project. So you can ask them, and they got it. They got the concept correct. Although we will see tomorrow. I will see with Pak Aulia and Kak Devita whether they can demonstrate it or not tomorrow. Use their circuit to measure the resistance change due to this absorbed infrared. Because of course the absorbed infrared, the heat changes or the temperature changes at your CNT-coated thread due to the infrared absorption will be much smaller than due to the calibration that you made, yeah, inside the thermostat box, because that is due to the conduction, convection, etc. Now you are isolating it. You have to make sure it is vacuum inside, so the changes is just due to the infrared radiation. And the Fresnel lens as well. Yeah, see, look, this is how it works. Are you sure that you have put it correctly or not? So this is, yeah, the right side should be your what do you call it? This part should be where your hand is. And then the Fresnel lens will focus to, this is your CNT coated thread. You understand? You should not put the other way around. Yeah, this is the difference with zinc selenide lens. The zinc selenide sign, you can, it works on both sides. You can flip it around from either way, it will be focused. But Fresnel lens work one way, like this. This is supposed where you should put your hand, and it will be focused towards your CNT coated thread. Are you sure that you have put the Fresnel lens in this direction?
Actually, the
Sir,
Fresnel lens.
can I ask? Itu yang light source itu maksudnya gimana sih? Aku
So
kurang
this
ngerti
is
gitu kayak
this is
kenapa taruh
in this
mana.
one, it is used as a spreader from a light source spread to be a collimated light, yeah, like this. But in your case, you want to focus the radiation from your hand into the sensor in the middle of your absorbed HPN fabrics. So you have to use like this. So this part, this is should be your box. This is your box. This is your sensor. Your hand is outside. So this is inside. It's outside. Not like this. In this particular picture, the light source is this. This is functioned to make a collimated light with parallel with front from a single light point source. Light source point.
Okay, understood, sir.
Huh?
Ngerti.
Yeah. So my question then, during the your positioning of your Fresnel lens in your device, have you made sure that it is in the correct direction or not?
We weren't sure because we thought actually the Fresnel lens is.
Can you speak a little bit louder, Andy?
We think that the Fresnel lens harusnya cembung or cekung, yeah. But Fresnel lens that we get is not cembung and cekung or cekung at all.
Yeah, the Fresnel lens is, if you see here, it consists of this concentric. It has some groove, what we call as groove, like this. It is not one cembung, convex or concave. No, that is the difference with the usual lens. The usual lens, what you have is either a convex lens like this, or concave lens like this. Yeah, but in Fresnel lens, you have like this, a lens with a groove, concentric groove. Groove, you know groove in English? Yeah. Yes, something like that. This is the Fresnel lens used in passive infrared sensor, the motion detector. Yeah, they can capture even from far away your heat your heat, body heat, and then detect it as an increase in temperature. So that's what I want you to use. Yeah.
We didn't actually make sure that, and I think it the focal length to affects our results too. That's why perhaps that's I think that one of the factor that our bolometer shows
Low sensitivity.
Yeah, low sensitivity results.
Yeah, so please that is the importance of getting to know the theories, yeah, of the components as well. Yeah, not just immediately assemble them, but you use the theories that you have learned in sensor measurement, in electronics, as well as looking the details of each of the component. Yeah, the Fresnel lens, and the many other things. Otherwise, yeah, no significant improvement compared to the previous work by your senior. Okay. I will conclude it just now because time is already. Please later take into account all the inputs from myself, Pak Aulia, Devita, and also the other groups. And I will put in the Google Classroom the deadline for submitting the report. I hope I will put enough time for you to write the report. Any other questions, comments, Pak Aulia, Kak Devita, also from the.
No, I think from me is enough, Pak.
Yeah.
From me as well.
Okay, Kak, any from the students? Any other comments?